Okay, so today we are gonna start with the inverse image. Why we are doing this? Because this is very important to understand the measurable functions. Okay, so we say that let f from x to y be a function with a is a subset of y. Then we define the inverse image of the set A, which is a subset of y, is x belong to x such that f of x belong to a. Okay, so this is the inverse image. Now we are gonna have some algebra of inverse image. Okay, so algebra is definitely we will assume that let f from x to y with a is a subset of y. Then okay, so then the first thing is the first proof we're gonna do is that f inverse of y, okay, the complement of actually a is nothing but this is actually x f inverse of a. Okay, so for we know that for every a belong to y. So proof, if we are gonna prove this thing, very easy. So to because so these are functions, so function means that okay, so we will take the element from one side and then we will say that it belongs to the other side. So to do that we say that let x belong to f inverse of y a. We just need to use the definition. We say that okay, x, any set any element x is belongs to this. Now we want to show that what we need to show that actually x belong to the complement of f inverse a. This we need to show. And how can we show? We just need to use, and we need to actually show two inclusion, but we can do that just very easily. So if we say that let x belong to f inverse of y as a complement of a, what does this mean? It will go both way. So what if x belong to, so definitely this means that the f of x belong to the complement of a. We need to keep this inclusion. Okay, now if x belong to the complement of a, what does mean? If I say any element x belong to set a, in other words it says that the element will not belong to the complement of that set. So from here I can say that f of x doesn't belong to the set a, because if it belongs to the complement, this means that the set will not belong to the set a. Now what does this mean again? If f of x doesn't belong to a, this means that actually the element x doesn't belong to the inverse image of f a. Now what does this mean? Again, if x doesn't belong to the inverse image of a, it means that x will actually belong to the complement of f inverse a. What is the complement of f inverse a? Definitely it is x f inverse a, and that's what we showed. And why I was just putting the inclusion sign, both inclusion, because to show the other way we will start from here, that let x belong to x, and then definitely we will go to this step and then so eventually. Okay, so that's very easy. Now the b is f inverse of union of I belong to index set I. ei is actually union of I belong to, we can put outside this union of f inverse of ei. So proof, again we will say that let x belong to the f inverse of union of I belong to the index set ei. Now again we need to show that we need to show that x belong to the union of I belong to I, f inverse of ei. How can we show that? So we will start from here. So if x belong to this thing, this means that f of x belong to the union of I belong to I ei. Okay, that's just, you know, the it will go both way. Okay, so f of x belong to the union of I. What does mean when an element, when I say a belong to the union of, you know, I belong to I ei, this means that it will belong to one of the ei. So this means that f of x belong to ei for some I. Okay, for some I belong to I. If it was intersection, this means that f of x belong to ei for every I belong to. But now it's, since an element belongs to the union, means that it will belong to one of the. It can belong to both. It can, but the minimum question is belong for some I. Okay. Now what does this mean? F of x belong to some of ei means x. What? So x doesn't belong. X belongs to the f inverse of ei for some I. Okay, and we are really close to our target. So what does it mean? If I say x belong to, you know, a set for some index, so this means that the element will belong to the union of this thing, and that's what we need to prove. So we are done. Okay, and the third c is, again we need to show that f inverse of intersection of I belong to I ei is nothing but this is intersection. Again we can put that outside of ei. Okay, so again for proof, what we are gonna do, so for proof we will again assume that let x belong to f inverse of intersection of I belong to I ei. Need to show that x belong to the intersection of f. So this means that if x belong to this thing, so the inclusion will go both way. So this means that f of x belong to the intersection of I belong to I ei. Now if f of x belong to the, if any element belong to the intersection, this clearly means that f of x will belong to ei for each I belong to I. For every, if I say an element belong to the intersection means it will belong to the every set. Okay, now what does this mean? This means that x belong to f inverse of ei for each I belong to I. Now what does this mean? This means that, okay, x will belong to the intersection, because if belong to each I, this means that each intersection, and we are done. Very easy. Okay, very like easy thing to prove. I think you don't need to worry about anything. Okay, so now another proposition, this is called the composition of the inverse images, that let f from x to y and g from y to z with I would say again with E is subset of y, then the composition of g of f inverse of the set E is nothing but this is f inverse g inverse a. Okay, sorry, this a is definitely the function of is a subset of z, sorry, like very obvious. Okay, so now to prove that, what we are gonna do, again we will take an element x. So let x belong to the composition of g and f inverse a. We need to show that x belong to f inverse g inverse a. Very easy, again both inclusions, but again easy to do that. So if we say that x belong to the composition of g of f inverse a, this means that g o f of x belong to the set A. Now what does this mean? This means that what is g of f of x? This is g of f of x belong to a. Now again, what does this mean? This means that f of x belong to g inverse of a. Again from here, what can I say? X belong to f inverse g inverse a. And that's what we proved. Very easy.